Hi, and welcome to section 7.1, the central limit theorem. In this section, we're going to be talking about how if we do enough samples, we end up with a normal distribution again, basically. All right. So let's suppose we have some random variable x, and it has some distribution that we may know or we may not know. It doesn't matter. And we're going to define a few new things. We're going to have mu sub x be equal to the mean of our random variable, and sigma sub x be equal to the standard deviation of our random variable. So we're going to make sure that we're using subscripts that match the random variable so we can make sure we keep those intact. And if we take this random variable, we draw random samples of size n from this random variable, a new random variable x bar, which consists of the sample means, will tend to be normally distributed with the mean the same as the original mean and a standard deviation equal to the original standard deviation divided by the square root of it. Let me go into this a little bit in more detail. So this is the central limit theorem, and what it says is that if you keep drawing larger and larger samples and calculating their means, the sample means themselves will form a normal distribution. And this normal distribution, the sampling distribution, has the same mean as the original distribution, and its standard deviation is the original standard deviation divided by the square root of your sample size.
All right, here's an Excel simulation I did so we can really jump in and investigate these sampling distributions. So my brain just stopped there for a second. So my first example here is just a regular distribution, a regular discrete distribution of rolling a die. So here are my die rolls, and they go down here. I have a ton of them, like 500, and I just had them generated. Each time I roll a die, I take the mean, which in this case is just going to be the value because there's nothing to average, right? And as you can see for the histogram, all the ones, the twos, the threes, the fours, the fives, and sixes all have about a same equal chance. All right. The average value is 3.5, which is what we would expect from this distribution that has values 1, 2, 3, 4, 5, and 6, all with probability 1/6. So our mean is going to be about 3.5 for this. Straightforward stuff. We haven't done anything different here. So what we're going to be doing next is we're going to just take larger samples. So let me show you what that means. When I say this is sample size 1, there's one item that we're computing. Going up to sample size 2, what does this mean? It means I'm going to roll a die twice and I'm going to take their average, okay? I'm going to take their mean. And that is what I'm going to do a distribution on. The mean could have any value from 1 to 6 still. If you got both ones, it would have a mean of 1. There's 1. If you got both sixes, it would have a mean of 6. So all the values are still possible. All right. The average value is still going to be 3.5. The mean hasn't changed. Okay. And the reason that is because you can see that the middle values are happening with a higher probability, but it evens out when you multiply the higher numbers by the higher probability. So the average is still 3.5, same thing. But what you'll notice is the standard deviation has decreased, all right? So that means there's less variance in the data scores. More of the data scores are in the middle. Remember, smaller standard deviation. More of the data scores are near the mean and less are near the edges. And that makes sense because we're averaging things out, right? Let's average things out a little bit more. So let's roll 4 die, take their average, and then build a distribution on the mean of those 4 dice rolls. Again, we're averaging out even more now. For there to be a 1, it has to be a 1, 1, 1, 1, right? That's not going to happen very often. For it to be a 6, it has to be all 6s. You can see these middle scores are becoming more and more likely. And in fact, it's looking more and more bell-shaped. And our mean is still 3.5, more or less. And our standard deviation has gone down even more, right? The data is less spread out. The data is more grouped about the mean. And finally, one more. This is with 10 dice rolls averaging out and looking at the distribution of these averages, the sampling distribution. We take a sample of size 10 to compute our mean. It's even more dramatic. Same mean still, even smaller standard deviation. So that's what we're doing here when we're talking about these sampling distributions. The more values we have in the sample, the more things average out and the more likely we are to just get the average value, to just get the mean. Standard deviations get smaller and smaller, but the mean stays the same.
Okay, so to put it formally, if you draw random samples of size n, the distribution of the new random variable x bar, the sample distribution, which consists of data values that are sample means, is called the sampling distribution of the mean. And the sampling distribution of the mean approaches a normal distribution as the sample size increases. So let's do some examples. Let's say we have an unknown distribution of mean with a mean of 90 and a standard deviation of 15. From this distribution, we're going to draw samples of size n and calculate the mean. Okay? So we do size n, calculate the mean. Let's find the probability that the sample mean is between 85 and 92. So the mean is going to be between 85 and 92. First of all, let's go ahead and define x bar. What is n? What is mu sub x? What is sigma sub x? And let's fill in the blank for a sampling distribution. Well, x bar is a mean of a sample of size 25. So you have 25 samples and you find their mean. So n is equal to 25 because that's our sample size. Our mu sub x is 90 because the means are the same. And our sigma sub x is 15 divided by the square root of 25 because 25 is our sample size, and we use the formula sigma divided by square root of n. Right? So x bar is distributed normal 90, comma 15 over root 25, or 90, comma 3. To find the probability that the sample mean is between 85 and 92, we're just going to use Desmos again. I'm not going to walk you through that. We've been doing that. We did a normal distribution with mean 90 and standard deviation of 3, and we found the probability the sample mean was the probability that value, the value of the sample mean, is between 85 and 92 to be 0.699, about 70%. All right, let's do another example. Let's say we have okay, so we had the same situation, same example. Sorry, I forgot what I was going to do here. On same distribution, mean of 90, standard deviation of 15, samples of size 25 are drawn randomly from the population. We want to find the value that is 2 standard deviations above the expected value of 90, the sample mean. So what value would be 2 standard deviations above that? Well, remember our new standard deviation is going to be equal to 3, or 15 divided by the square root of 25. So a value is going to be 90, our mean, plus 2 of our new standard deviations, so that's going to be 96. It's the value that is 2 standard deviations above our expected value, our expected mean. Let's do another example. The length of time in hours it takes a group of aged 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. Of all those games, okay, all those games we have recorded, their times, how long they took, we're going to draw 50 of them out from the population. And we want to find the probability that that sample mean from that sample size of 50 different games is between 1.8 hours and 2.3 hours. All right, so what are we going to do? Well, normal dist. Our mean is still the same. It's still 2. The only thing that's different is our standard deviation. The standard deviation of the actual game length is 0.5 hours. The standard deviation of our sample, of our sample mean, is going to be 0.5 hours divided by the square root of n, which we said is 50. So 0.5 divided by the square root of 50, and actually I just put it into Desmos like that. I didn't bother to calculate it. And we get an answer of 0.9976. All right, so let's do an example comparing the distribution itself with the sampling distribution. So in a recent study, well, not too recent, October 29, 2012, on the Flurry blog, the age of tablet users was given as normally distributed with a mean of 34 years and a standard deviation of 15 years. We're going to do a study that takes samples of size 100. So let's first by looking at what are the mean and standard deviation for the tablet users themselves. So if we actually just looked at the tablet users, what is their distribution? Well, if X is the age of the tablet users, the mean of X is 34 years, and the standard deviation is 15. All right? And X is distributed normally, 34, 15. Let's find the probability that a tablet user's age is more than 30 years old. Using Desmos, we're going to do a normal distribution, 34, 15, starting at 30 and going to infinity. The probability that it's more than 30 years old. Okay. So that gives us about 60%, 60.5%. Now let's look at the sampling distribution. All right, same study. Now we're going to do samples of size 100. what are the mean and standard deviation for the sample mean ages of the tablet users? So of all those samples of size 100, and we calculate the mean, that new distribution, what does that distribution look like? Well, remember the means stay the same, so it's still a mean of, the mean is still 34. Oh, I don't know what else I can. So X bar is now the mean of a sample of size 100. The size of the sample is 100. These are things we need. The mean stays the same. It's still 34. Sigma was 15 for the normal distribution for the ages of the tablet users. So the sigma X for the sample sampling distribution is going to be sigma divided by the square root of n. So 15 divided by the square root of 100. So this distribution, the distribution of sample means, is normally distributed with a mean of 34 and a standard deviation of 1.5. All right. So now let's find the probability that the sample mean age is more than 30 years. So that means if we had a sample of size 100 and we took that average, the probability that average is more than 30 years old. So we put it into Desmos, our good pal, 34, standard deviation now 1.5. The probability goes from, we're going to compute over 30 again, so 30 to infinity. And now the probability is much, much smaller. Well, that's because each one of the values in the sample mean is 100 users worth of data, right? The average of 100 users. So it's not just that one user is more likely to be older or younger, but that the average of all those 100 users is over 30 is very unlikely. So just like with normal distributions, you can find the percentiles the same ways with this. It all still behaves just like a normal distribution. So if we want to find the 95th percentile for the sample mean age, we would use inverse CDF and Desmos just like we did before. Normal dis 34, 1.5, putting in our percentile. And the 95th percentile for the sample mean age, the sample mean age is 36.5 years. If you went back and calculated the 95th percentile for just the tablet user's age, it would be much higher than that. Because remember, we're averaging all those 100 ages. All right, well, this is an introduction to the central limit theorem. We're going to be working with this a little more as Chapter 7 continues. Enjoy.